Hello, my name is Johnathan Berumen, and today I will be presenting my real-world static analysis project for MECH 1321. In this presentation, I will be analyzing a light post to determine whether or not the specific structure is able to withstand the wind loads it is subjected to. I will utilize the theories of mechanics statics in order to prove or disprove the structure's equilibrium. Please keep in mind that key details and important assumptions will be discussed in this video only. All minor components can be referenced in the technical solution provided as a PDF document. At first glance of the structure, we are able to see that it is supported by welds from two angle iron pieces. This support is known as a fixed support in statics. The black arrow points to the fixed support. The structure also contains a lamp comprised of two materials. The purple arrow points to a type of glass, while the yellow arrow points to an unknown metal. For this project, I will denote the knowns as parameters that can be easily obtainable. The knowns of this structure include the wind load, the dimensions, the weight of the lamp, as well as what type of support the structure has. We will also need to find the moments about the support, as well as the support reactions caused by the wind load. The free body diagram I drew was designed with simplicity in order to keep the focus on the forces acting on the lamp. The wind load is directed in the J direction to maximize the support reactions. I will denote the fixed support as point A, shown in the free body diagram. Because a fixed support does not allow rotation, it will create a couple moment along with two support reactions. The reactions in the moment are shown as RAY, RAZ, and MA respectively. The weight of the lamp is directed downward in the Z direction. The dimensions displayed on the diagram were measured using a measuring tape and converted into meters. In order to perform the problem, I will calculate the knowns. I started with finding the entire weight of the lamp. Through research, the lamp was found to be made of aluminum and silicate glass. I was able to find this through multiple sources, including the patent document found under the patent number searched. With this information, I was able to find the density of each material. I then decided to simplify the lamp into three basic components. The volume of each component was found and multiplied by its density to obtain the mass. The figure to the side shows one of the components I calculated the mass of. I then proceeded to do this with all other components of the lamp and added all of their masses together, shown below. Once the total mass of the lamp was computed, I converted it into newtons. I found the weight of the lamp to be 32.3 newtons. Once the weight was found, I decided to calculate the wind load applied to the lamp. An article posted in 2016 shows that the strongest wind recorded in El Paso was 69 miles per hour. I then utilized an air density calculator in order to find the density under average conditions of El Paso. Once that was done, the surface area of one side of the lamp was then calculated, which is shown below. Once all three variables were found, I utilized the wind load calculator in order to find the wind load. The wind load came out to be 42.4 newtons. The pole of the lamp was assumed to be steel. This is because I confirmed it was a ferrous metal using a magnet. It also had rust on some parts of it. Steel is known to have a tensile strength of about 320 megapascals. Once all variables were calculated, we can start to solve the problem. First, I identified the knowns and unknowns. Secondly, I determined the moment about point A in relation to the x-axis. The calculations can be seen on the right side of the screen. Then, I analyzed the support reactions along the z-axis as well as the y-axis. Some of the limitations I encountered while doing this project included no specific dimensions I could find for the wind load force, as well as the lamp was simplified to better calculate the weight. and become less of a tedious process while calculating it. Lastly, the drag of the wind load was not accounted for. And although this project was completed with as much accuracy as possible, there were a few limitations, such as the ones mentioned above. After calculating all of the forces, we find that the support reaction in the J direction equated to 42.4 newtons. The support in the K direction is 32.3 newtons. And lastly, the strongest force was the moment due to the wind, which was 70.8 newton meters. From source 7, we can see that the tensile strength of steel is 320 megapascals, which translates to about 320 million newton meters squared. This means that the 70.8 newton meters force will not lead to failure in the static structure, and equilibrium is confirmed. Here are my references, and thank you for watching my presentation.